OCR Statistics, Discrete Random Variables 2, Binomial and Poisson Distributions. This is video 2.5 and it's on the properties of the Poisson distribution. In the previous video, we looked at an example in which the average number of cars passing a point on a road in a 5-minute period was 4. So we defined the parameter, lambda, to be 4. We had to answer a question that was finding the probability that in this 5-minute period exactly 2 cars went past. So what we did was we modelled this as a Poisson distribution with parameter 4. And we used our calculators to calculate the probability that x was 2. Now remember, you can use your calculator for this. It's the Poisson PD function that you need, or you can use GeoGebra. And in this case, it turned out that the answer was 0.147. Now, what if we change the question? So in this case, we're looking at the probability that in a 10-minute period, exactly 2 cars go past. Now, it is quite tempting to think, okay, well, the time has doubled here. Maybe we can manipulate the probability in some way. But we're not able to do that. What we must do is think about changing the parameter. Now, remember, for a Poisson distribution, the average number of events in a given interval is fixed and finite. And what this means is the rate is proportional to the interval. So if we scale up the interval or down, then the value of lambda must also be scaled. So for example, if we have 4 cars in 5 minutes, we would expect 8 cars in 10 minutes. So let's go back to that question again. So we know that in 5 minutes, the average number of cars is 4, and we have to find the probability this time that in 10 minutes, exactly 2 cars go past. Well, let's say again that we're going to model this as a Poisson distribution. I'm going to use a new random variable now because we've got a different time interval. Now, in this case, we've got to find our new lambda. So because the time has doubled, this means that we would also double the 4. So we would expect 8 cars in 10 minutes. We want to find the probability that this is 2. Now again, you could use GeoGebra or you could use the Poisson PD function on your calculator, and you will get an answer of 0.0107 to 3 significant figures. Now remember, previously in the 5 minutes we had 0.147. So just look at how much smaller our answer is now. Now let's look at another example. In this case, that we're told that the average rate of flaws occurring in a roll of dress material is 0.4 flaws per meter. And we have to find, first of all, that there are no flaws in a 1 meter length. Well, in our question here, we know that 0.4 flaws are happening in 1 meter. And this question is also about 1 meter. So lambda will remain as 0.4. In the second part of the question, we're interested in finding 1 flaw in a 3 meter length. So the length here has been tripled, so we must do the same to the 0.4. So lambda in this case would be 1.2. And finally, we're looking at a half meter length, so we'd have to half the 0.4 to get 0.2. Let's look at answering these questions now. So in the first case, we were told that we wanted no flaws. So we have to find the probability that x is 0, and we're using our lambda as 0.4, and this will give you an answer of 0.670 to 3 significant figures. The second case, we were asked to find exactly 1 flaw, so this would be y equals 1. and that gives you an answer of 0.361. And finally, we were asked to find again one flaw, and this was for a half a meter, so lambda was 0.2, and this gave us an answer of 0.164. So just double check that you're able to calculate those values using your calculator or GeoGebra. Now let's look at what happens when we need to add Poisson variables. So for example, if x was the number of cars passing in 5 minutes and y was the number of vans passing in 5 minutes, if we're interested in finding the probability of the number of cars and vans passing, we're able to just add our two parameters. And this feels quite intuitive. Okay, so let's look at an example about this then. Say for example, again, this was cars and vans, and we had the parameter 1.2 for cars and 0.7 for vans. And we wanted to find out what's the probability that exactly 3 pass in 5 minutes. This is what this could mean. So we would define a third variable, which would be x plus y. Okay, so this is the number of cars and vans together. And we would model this as a Poisson distribution. Now, because we've combined the cars and vans together, we would need to do the same with the parameters. So the parameter would now be 1.9. So we want to find the probability that W is equal to 3. Again, you can do this on your calculator. You can use GeoGebra. You can also use the formula, which we're going to look at on the next page. And this will give you an answer of 0.171, and that's to 3 significant figures. So here it is written out neatly. You can see our new parameter is 1.9 here. And in this case, it shows how the formula could be used. But obviously, you get the same answer whichever way you do it. Now, you could check that this is correct by actually working out all of these individual probabilities, multiplying them, summing them, and you will get the same answer as you got previously. So you could use this to check if you wanted to. So this was 2.5, the properties of the Poisson distribution, and the next video is 2.6, which is on the mean and variance of the Poisson distribution.